Okay. Now, guys, before we start, I want to say that if you printed out the slides like before the weekend, what I have up here is going to be slightly different in certain little places because it was over the weekend that I caught these little places in Chapter 7 that had material that is no longer covered on the AP exam. And I sincerely apologize, when we started Chapter 7, there were a whole bunch of equations on all the slides, and I kept saying, don't worry about it, don't worry about it, it's on your equation sheet. Well, I was mistaken, okay? On the front side of your equation sheet, there is a very small little section called atomic structure. You'll notice that there's a lot of blank area in there. There's only 2 equations in there, okay? So many of those equations that I had up on the screen are not on your equation sheet, but you don't need them, okay? Calculating the mass associated with a certain amount of energy, no longer covered, so don't worry about it, okay? And remember, if you ever forget, and this goes for the entire equation sheet, if you ever forget what a variable represents, if you just scan your eyes over to the right, they're always defined there. And if it's a constant, the constants are also given to you. Okay? So, for those of you that may have printed out the slides early, this slide actually had 4 questions on it, but I took one of them out. So, using the 2 equations that are given to you on your equation sheet and the constants associated, please solve this problem, these problems. Remember, you can express a frequency in either one of these units. They're the same thing. An inverse second or hertz, your choice. Okay? And I realize some of you may have, instead of using this very precise number, you may have just put in 3 times 10 to the 8th, and that's fine. I believe that actually gives you a rounded answer of 385,000 hertz, and that's fine. Your choice. It really doesn't make a difference. Please don't overthink number 3. Look at what you solved for in number 2. This is the energy of a photon, 1 photon. How many photons are in a mole of photons?
6.02 times 10 to the 4.
Yeah, Avogadro's number. So how do you suggest I solve number 3? Take your answer from number 2 and multiply it times Avogadro's number. For those of you that have an older copy of the slides, there are many more other equations. You don't need to worry about those. And I'll tell you, this is the extent of the math in this chapter. That's it. Okay? I want you all to be aware that second quarter, in general, is a very conceptual time. For those of you that are math enthusiasts, don't worry, we will be back in the land of math with a vengeance in third quarter, so don't you worry.
Oh.
Now, ladies and gentlemen, the remainder of this chapter moves away from this broad electromagnetic spectrum. The remainder of this chapter starts to really zero in on visible light and what's causing it. So really, the remainder of this chapter, if you wanted one big heading, it would be, what are electrons doing? Okay? The remainder of this chapter really has to do with the behavior of electrons, how we classify them, how we organize them, that kind of thing. Okay? Now, today's essential question, where does light come from? Well, light is a product of the behavior of electrons. Okay? And there are two terms that I'm going to start off talking about, and these are their definitions, but I think they'll be easier understood if I explain it to you with a picture in front of you. Okay? Anytime you see the term continuous spectrum, what that means is all colors of the rainbow, all wavelengths of light. Okay? And when most of you were probably in elementary school, your teachers may have taught you a little mnemonic device to help you remember the order of the colors in the rainbow. Roy G. Biv. I don't like Roy G. Biv. I prefer Viv G. Yor. Okay? Now, does it really matter what order you know them? No. Okay? The reason that most chemistry textbooks will have them listed in this order, as opposed to the other way around, is because this puts the colors in order from short wavelength to long wavelength. Violets, indigo, blues have shorter wavelengths. Reds have longer wavelengths. Now, if you put them in order of Roy G. Biv, that would be listing the colors in order of increasing what? Frequency, or what else? Energy. Energy. Okay? Reds, low frequency, low energy. Violets, high frequency, high energy. Okay? So, does it really matter what order you remember them in? No. Okay? As long as you remember the characteristics of each type of light at the end. So this is called the continuous spectrum. What's shown down here at the bottom is called a bright line spectrum. And we are not seeing all wavelengths of light. We're seeing only specific wavelengths of light. That's what these numbers down here at the bottom represent. These are lengths in nanometers. And what we are seeing here, maybe this is one particular element. Okay? So from any one particular element, okay, or atom, or let's be even more specific, electrons within an atom, you're not going to see all colors of the rainbow. You're going to only see specific colors. Right? Now, where is that coming from? Let me tell you. Right? This diagram right here, this is called the Bohr model of the atom. We've got the nucleus in the center, and what do we call these rings? Energy levels. Energy levels. Okay? And according to the Bohr model, which by the way is not today's model, okay, the electrons sit on these energy levels and they orbit the nucleus, okay? Now, it's not that that's incorrect, it's just not quite complete for what today's model shows us, but we'll get to that in a second. Okay, the first thing I want to just make sure is clear is you see visible light because electrons are falling down energy levels. Okay, when electrons fall from a high energy level down to a lower one, energy is released in the form of visible light. Now, okay, these terms should be familiar to you. You should have learned these terms in Chem 1. Ground state versus excited state. Okay, ground state, I almost wish I hadn't put this n equals 1 in here. Ground state means an electron is as low, and when I say low, I mean close to the nucleus. An electron is as low as it can get. That may not be on energy level number 1. Maybe the lowest possible level that an electron can get is energy level 2. Maybe it's 3. The point is, it's as low as it can be. And then this one, I always think of like being at some kind of sporting event, okay? If you're at a football game, for example, and your team scores a touchdown, nobody in the stands, when your team scores a touchdown, goes, yes! And gets right down to the ground. Nobody gets excited by shrinking down to the ground, unless they're like passing out or something. Okay?
Just that shy.
What do people do? They stand up out of their seats and they put their hands in the air. Yes! Okay? They're excited. Excited means an electron has jumped up. And when I say up, I mean away from the nucleus. And how does it do that? It absorbs energy. Okay? So let's be clear. To move an electron from ground to an excited state, the electron must absorb energy. When it moves from excited back to ground state, it would do what? Release in the form of light. Okay? Now, I don't know that every Chem 1 teacher does this lab, but most of you will have done this lab. We like to do a flame test lab in our Chem 1 classes, where you put things in the Bunsen burner and it changes the color of the flame. Okay? What color does a Bunsen burner usually burn? Blue. Okay, it should burn blue. When we've done this flame test lab, and this is in case you haven't done it before or you don't remember, we have these little wooden sticks. They're called wooden splints. They're just like popsicle sticks. And we soak them in different ionic compounds that have different metals. We let them soak overnight, take the sticks, and then we hold them in the Bunsen burner flame. Now let's think about what's happening here. You put the stick into the Bunsen burner flame. The electrons in all the atoms absorb energy from the flame, which takes them from here to here. But this is a very unstable position. Those electrons can't stay there. So they fall. And they release light. And in this lab, we saw some elements release red light, some yellow, some green, some blue, some purple. Okay? All these different colors. And let's talk about why you see different colors. Okay? And we're going to have a couple of these today. I'm going to use one of Miss G's famous ridiculous and stupid analogies. Okay? I want you to imagine for a moment, if you will, that I have just for some reason just totally lost my mental capacity, and I decide that it would be a great idea to just open this window, shimmy out the window, and I just fall down on the ground outside. Why would I do that? I don't know.
Prove a point?
Will I... Do you think if I shimmied out that window, am I going to break a bone?
It'll hurt.
Probably not. It'll hurt. Mostly my pride. Okay? But I'm probably not going to hurt myself. What if I did the same thing in an upstairs window? It's going to hurt more. Could break a bone. Probably not going to kill me, but I'm probably going to break a bone. What if I did the same thing out of a 20-story window? Yeah, I'm good. I'm dead. Okay?
Don't do it, Miss G.
Thanks. Thank you. I appreciate that. Thank you. Can you tell me in which situation am I hitting the ground with the most energy? 20-story. Okay, fine. Take me out of the picture. Now let's bring it back to electrons. If an electron falls a long distance, it will release a high amount of energy. Folks, which end of the rainbow, red or violet, has high energy? Violet. So in this flame test lab, when we could see purples or indigo colors, we were seeing electrons falling through more energy levels. If an electron falls just a short distance, maybe from just energy level 3 down to 2, light is still released, but it's lower in energy. We're going to see more reds, oranges, things like that. Okay? When we would see greens, you're seeing sort of intermediate falls. But that's why you get different colors. These electrons are falling different numbers of energy levels. Okay? And they can't fall like a half an energy level. They can only, fall whole numbers, integers. Okay? Does that make sense? Okay. Now, there is an equation on this slide that is not on your equation sheet, that is not on your problem set, that will not be on the test either. So why did I leave it in? Well, I left it in to illustrate a point. First of all, I apologize, this did not come through very well. There is a division sign right there. It is very, very faint. I don't know why it is so faint, but there is a division sign there. For those of you that are math inclined, I left this slide in there to prove a point to you from a mathematical perspective. This is an equation you would use to calculate the energy, that's what E stands for, at a particular energy level. Like, this represents an integer, like energy level 2 or 3. What I would like for you to do, we're going to just do this together, it's real quick. I would like for you to put into your calculator the numbers to calculate the energy of an electron sitting on energy level number 4. Put that calculation into your calculator. We're going to do this together. Did you all get that? Okay. I want you to do the same exact thing, except this time I want you to calculate the energy on level 2. Put 2 in for N. Okay? Now, I care less about the energy content of these electrons at each individual level. What I care more about is the difference between them. Okay? This was the energy at our final energy level. This was the energy at our initial. Final minus initial. What do we get? change in energy, I get this. Okay? Now I care less about the number, but more about the fact that it is negative. What does a negative energy mean to you? Exothermic. Energy is released. Well, guys, think about what we just did. An electron fell from 4 to 2. I'm mathematically proving to you that energy is released. Okay? And if I really wanted to, we're not going to do this, but what they used to do on the AP exam would be to take this energy, plug it into this equation, solve for a frequency, and figure out what color light that would be. Okay? We don't do that anymore, but we used to do that. We're still talking about light, okay? For any of you that were in honors chemistry, and you did the water testing project, this term should, or may be, familiar to you. Spectroscopy. Okay? That is a technique that we use in our water testing project. Okay? And let me just explain to you what's going on. In a spectrophotometer, okay, it's a machine, you put a sample of some solution. And remember, the word solution implies something has been dissolved in something else. Okay? We shine a beam of light through it, and depending on how much light gets through the other side, can give us an indication as to how concentrated the solution is. Now, what do I mean by a concentration? What's another word for that? Molarity, okay? And, I mean, think about this in your everyday lives. Let's say you're making a glass of Kool-Aid from the powdered mix, okay? And the directions say, you know, for a 8-ounce glass of water, add 1 scoop of Kool-Aid mix. Well, that's too sweet for you. So you're like, nah, I'm just going to add a half a scoop. If you add a half a scoop, think about what that would look like. Would your glass of Kool-Aid be really, really, really red, or sort of clearish? Clearish, okay? If you were to shine a flashlight through that, a lot of the light would get through because there are not as many dissolved particles to break up that light. So if I shine a light through this watery Kool-Aid mix, most of the light's going to get through because the Kool-Aid is not very concentrated. What's the opposite of concentrated? Dilute. Whereas if you're a person that likes your Kool-Aid sickly sweet, like so sweet, you don't even scoop it out. You just pour water into the container. Okay? Your Kool-Aid is going to be like electric red. And if you try to shine a light through it, there's pretty much no light that's going to get through. Okay? Because it is so concentrated. And guys, there is an equation for this. It is on your equation sheet. It is on the back, right here. It's the one that says A equals ABC. Okay? Usually, this lowercase a, the absorptivity and the distance, usually these two values will be given to you. You are typically either solving for the absorbance or the concentration. And to be honest, usually you're going to be solving for the concentration. Okay? And there is a direct relationship. And think about it, it should make sense. Absorbance means how much light is sucked in, like not getting through. The more light that is absorbed means this is a more concentrated solution. Okay? And I'm not even going to go through example problems with this because it is literally just plugging numbers in and solving. And that's it.
So we should be thinking about light in terms of it being absorbed rather than the particles reflecting?
In this case, yes. When light is absorbed, that's an indication of concentration. Okay? Now, this slide gets into what today's model of the atom looks like. It's called the quantum mechanical model. Here's the gist, guys. If you remember, a couple of slides back, we had a Bohr model that looked like a bullseye, like this. Okay? What were the rings called again? Energy levels. The Bohr model says electrons sit on these energy levels and they go around the nucleus like planets go around the sun. That's not quite correct. Okay? Electrons do exist on energy levels. They do orbit the nucleus, but they don't orbit them in nice, pretty little circles. Or even ellipses like a planet. Okay? Let's go back to the beginning of this chapter. What do we say in chemistry? What is light? What is it? A photon. Photons, yeah, plural. They're traveling in a wave. Okay, well, what is a photon? An electron. Well, if photons, which are just a form of electrons, travel in waves, why shouldn't the electrons that are going around the nucleus also travel in waves? They do. So they don't travel in pretty little circles. They travel in waves. And here is where this word quantum comes in. Okay, the thinking is that when an electron is orbiting the nucleus in these waves, that an electron will complete a whole number of wave cycles. For example, on energy level 5, an electron will complete 5 wave cycles. On energy level 4, an electron will complete 4 wave cycles. You are never going to have a non-integer. Okay? An electron is not going to complete 4 1/3 waves around the nucleus. The word quantum or quantization means whole numbers, integers. Okay? Set amounts of waves. And that's the gist. If you want to know more, go talk to the physics people. Okay? But the thing is, electrons travel in waves and they complete whole numbers of waves. That's the important part. And last class, somebody asked me the question, for example, an electron that's on energy level 5, does it always stay in this perfect path? I don't really know the answer, but my gut instinct is to say no, because of what's called the Heisenberg Uncertainty Principle. Okay? And guys, the take-home message for the Heisenberg Uncertainty Principle is that we really don't know how electrons behave. We can make theories, we can make predictions, but we really don't know for sure. And I'm going to explain it to you, but I'm also going to give you another one of my crazy analogies. I want you to imagine that I move all the furniture out of my classroom, close the blinds, turn the lights off, and put you in here. There is no light whatsoever. Like, you can't even see your hand in front of your face. There is zero light. And I give you a task. I tell you, and you know how much I love balloons.
Oh, God.
I tell you that there is a helium balloon floating somewhere in this room, and your objective is to find it. Okay? And destroy it, of course. What are you going to do? You can't see anything. What are you going to do? How are you going to do this? Like this, right? All right, I'm waving my hands around. I'm trying to find it. Okay? Well, here's the thing. You're walking around the room. You're waving your hands around because you can't see anything. You're going by your sense of feel only. You're waving your hands around. As soon as you find it, because you are swinging your arms around, you've batted it away. So you found it, but now it's somewhere else and you've got to keep looking for it. So, okay, you feel like you batted it with your right hand and you know, we're moving this way, so you're like, okay, it's over here somewhere. All right. But the chances of you bringing your hands together like some sort of like Zen master, like, and just landing right on the balloon. No, that's not going to happen. Okay? You have to do something like this. So the act of you looking for it changed it. Okay? Let's bring it back to actual science here. All right? Let's say you are trying to observe this one electron, which I'm representing as my fist. Okay? You're trying to look at it through some very powerful microscope. So guys, to see anything, what do you need? A light. In order to see something, you need a light source. Well, what is light? Photons. Okay, let's say this light source is right over my shoulder. Okay, it's shining this way. I'm trying to look at this electron right here. I turn the light on, and out of the light bulb comes this, a photon, which is exactly the same size as this thing I am trying to look at. And then it's like you're playing pool, like billiard balls, okay? I'm going to say something very deep and philosophical. The act of observing an electron changes it. Okay? The act of you observing it changes it. Changes its position, changes its velocity, changes its momentum, changes a lot about it. If you want to know how it really behaves, you have to turn the lights off. But if you turn the lights off, then you can't see it. All right? So, do we really know how electrons behave in their natural environment? No, we really don't. They can make predictions, they can make theories, but we really don't know. All right, as fancy as this looks, this is a picture of what today's model of the atom really looks like. Okay? So you can call it the quantum mechanical model. What's another name?
Fuzzy.
Electron cloud. It looks like a cloud. Okay?
It looks like someone like having a nice model and then they put it to
The point is, folks, it's blurry, it's fuzzy, it's cloud-like, because we really don't know. That's called a probability cloud. Okay? Probability cloud because when I'm in this sort of light pink area, there's a certain probability of me running into an electron. And as I move closer into the center, okay, that probability goes up. It's a probability because I don't really know where they are. There's a chance of me finding one. So this kind of wraps up the whole visible light, how are electrons moving. We're going to move now into a phase of how are electrons organized around the nucleus. Okay, is your periodic table in front of you?
Yeah.
Yay!
Where's Henry Moseley?
I don't know.
Or Moseley.
Okay. Ladies and gentlemen, question. You need to know 2 historical names. Number 1, the first person to create an organized chart of the elements. Dmitri Mendeleev, a Russian. Okay? The first periodic table was organized by increasing atomic mass. If someone would please pick an element, any element. Gold.
Lead.
I like gold. Gold, element 79, look at it. Please tell me which number in the box on your periodic table for gold, which number is the atomic mass? 196.97, the one with the decimals. If you just scan your eyes from left to right across your table, I want you to notice that for the most part, today's table is also in order of increasing atomic mass. But if you look carefully, there are a few places where from one element to the next, the atomic mass actually decreases. Do you see any? Cool.
106 to 107.
All right. 106 to 107. What else? Okay, 108 to 109, 27 to 28, 18 to 19. Okay. The one I really want to focus in on is 18 to 19. Argon to potassium. I want you to imagine in the first periodic table, those 2 elements were switched. Think about that for a second. You've got argon, which is a gas at room temperature and has 8 valence electrons, a full valence shell, in the alkali metals, which are extremely reactive. And then you've got potassium, which is a metal that's soft enough to be cut with a butter knife. It's weird. But it is a metal with 1 electron, very reactive, in the very stable noble gas column. Is that not right? Okay. So, this guy comes along. I find it interesting that your textbook makes no mention of him whatsoever. This guy created your current one in order of increasing what? Atomic number. And when you put them in that order, that puts elements with similar chemical properties in the same families. And Mendeleev's table had similar property columns also, but there were some problems. Oh, good times, good times. Do you remember 1s2, 2s2, 2p6, 3s2, 3p6? Yes! Electron configuration. Guys, let me tell you something. Your periodic table that's in front of you is yours. You are welcome to color code yours, write things on it, whatever is helpful for you. You might find it helpful to label this area as S, P, D, F. Something that I find very helpful is I write in some numbers in certain places. Like on this little junction right here, I have a big number 3, 4, 5, 6. You may not remember why I have those there, but it'll come back to you. On this junction on my periodic table, I have a big number 4, 5, 6. Okay. These are representing energy levels. See if you remember, any of you. What energy level is the first one to have an F sublevel on it? 4. 4. Now, you may be very rusty with this. You may never have learned this in the first place. I hope that's not true, but I'm going to refresh your memory. Okay. Let's first just review a little vocabulary here, and we are going to do more practice with this next class, so don't fret. If you have an electron configuration written out like this, what do these big numbers in front represent? Okay, energy levels. The big numbers represent energy levels. What do the letters S, P, D, F, what do those represent? Sublevels. If you draw out your electrons, these arrows, we call that orbital notation, and we'll talk more about that next class. Do you remember what each box represents? An orbital. And each arrow represents what? An electron. So just reviewing a little bit of vocabulary. Okay, let's do some practice here. I'm going to pick the element cobalt. Element 27, I think. Yeah, 27. If I asked you to write the electron configuration for cobalt, how would it start as any of them start? 1s2, 2s2. Okay? Okay? Be careful. 3, 7. Okay? All right. You may need to go back and review this just a tad. Okay? Now, tell me this. If we kept going, staying on the same line, but let's say we went all the way over to element 35, bromine. How would this change? It would be 4s2, 3d, 10, then what? 4p5. Okay? Do you all remember that there was a shortcut? It's called the noble gas configuration. Look at where cobalt is and tell me what noble gas comes before it. Argon. And then we pick up from there. So what would it be? Okay. Now let me tell you guys, you lucky ducks, since you're in AP, you may always use the shortcut. Okay? Now don't get cute with this, people. If I asked you to write the configuration for a noble gas, yeah, this you cannot do.
LOL.
If I said write the configuration for argon, that's not going to cut it. You back up to the one before it and take it from there. Please try these. If you get it wrong, you get it wrong. Try it. I will tell you that, because I heard a couple of people saying, you know, what do you do if you have to go through the F sublevel? No longer on the AP exam. Because, and this one I truly do agree with, when you do take things through the F sublevel, or you're trying to do an element that is in the F sublevel, the configurations are so unpredictable that there's so many exceptions to the rules when you start getting in there that they just said, you know what, nobody should have to memorize that. Like, if I ever need an electron configuration for one of the low elements, I go look it up. Because they're so unpredictable, it's not worth making you learn it. Okay? Nor are quantum numbers on there either, if any of you remember those. Or any of the exceptions. I'm telling you.